This is the video for Lab 2, an Introduction to Organic Chemistry. For this lab, we're going to really talk about what it means to be organic, and then we're going to get into both the structures and the nomenclature of organic chemistry. Now, technically, we don't get into the really intricate details about naming. You'll get into that in organic itself, but for this semester, it's going to be a lot easier if you'll be able to recognize structures by their name or draw formulas from the name of an organic compound. Now, a lot of you haven't had organic in lecture yet, and so that's why we're going to cover some of that here. Now, we're going to talk about organic chemistry. We'll get into the different types of structures, and then specifically how to name everything. So organic chemistry is just the chemistry of compounds containing carbon. And so what that means for us is we're going to talk about hydrocarbons, which contain just hydrogen and carbon, as well as compounds that have things like oxygen and halogens attached. But anything that contains carbon is considered an organic compound. Now, when we talk about organic compounds, there's a few different ways to give information. So, for example, we could talk about C2H6O. That's the molecular compound, the molecular formula for a compound. But that doesn't really tell us how things are bonded. And so there's a few ways that chemists would want to deal with this instead. And so for us, probably the most detailed information you can get is from the complete structure. And so, for example, the way that I would draw a complete structure for a student is kind of like this. Now remember, hopefully you will remember from 111 or an introduction to 112 course, but all carbon has the ability to form 4 bonds. Its Lewis structure's got the dots here, and so it has room here, 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 and here for a specific bond. So when we make organic compounds, just keep in mind that all carbon is going to form 4 bonds. So this is a complete structure. I show all of the detailed bonds that are attached to each atom. It does not show bond angles because in general when you're writing on your paper it's hard to do that in any kind of space where you can still be able to write somewhat neatly. So this is the complete structure. If we wanted to condense it a little bit, the way that we're going to do it is it's really hard to write this. It takes up a lot of room. You can't write it on your paper just right. And really, these bonds can be simplified. So we could write the condensed structure as this carbon is bonded to 3 hydrogens. This carbon's bonded to this hydrogen, this hydrogen, this hydrogen. So CH123. Then, it's also bonded to this carbon, which is bonded to 2 hydrogens, so H2, and this hydroxyl group. So you can kind of get an idea of how we would do this. So the complete structure, say for, let's do butane. Let's go ahead and do the expanded. And so all of these are H's. So can you kind of see this is a little tiring to write out as a complete structure? It gets a little tiresome, especially the longer the molecules get, because honestly, we're going to be dealing with some really large molecules over the course of the lab and throughout the semester. So this is butane. Now it's going to be much easier to just draw it by carbon. So the condensed structure of this is going to be C, which is bonded to 1, 2, 3 hydrogens. and also bonded to this carbon, which is bonded to 2 hydrogens, which is bonded to this carbon, which is bonded to 2 hydrogens, and this carbon, which is bonded to 3 hydrogens. Now guys, I'm drawing the dashes in here just to kind of indicate, give myself some space, make it so that it's neat. My writing is not always the prettiest. So just keep in mind, sometimes you're going to see in your text, they're not going to include these bonds right here. It's just going to be kind of closer together. Now, over here I have a hydroxyl group that's kind of on its own. The reason I did that is just because it's how it's bonded. This carbon isn't bonded to 1, 2, and 3 hydrogens. It's bonded to 1, 2 hydrogens, and then bonded to this oxygen, which is attached to that hydrogen. So that's why I did it that way. So the condensed structure still tells us a lot of information. It tells us what atoms are bonded where. It's just a simpler way to do it. Now, in my lecture, I always say chemists are lazy, and so we want an even shorter way of getting information. And the way that we do that is with a line-angle structure. And here, you're going to have a line. Anywhere there's an end of a line, you can assume there's a carbon, and each carbon is going to have a maximum of 4 bonds. So going back to this, the only atoms you have to draw in a line-angle structure are non-carbon, non-hydrogen atoms. So for example, here, this has got a C, an imaginary C right here with 1 bond, so 2, 3, 4, makes it, all of these are hydrogens, right? And then it's going to be bonded over here to another carbon, hydrogens, 1, 2, 3, OH. The thing is, we're not going to draw that like that. That's too much work. So instead, we just know that the end of the line has a carbon, and it's going to be attached to the right number of hydrogens. And this end over here has a carbon, which is going to be attached to a hydroxyl. So you just kind of have to draw it like that. Over here, 1, 2, 3, 4 carbons. 1, 2, 3, 4. 1, 2, 3, 4. Assuming that this is going to have 3 hydrogens, because it already only has 1 bond. This carbon right here at this apex has 1, 2 bonds to other carbons, so it's going to have 2 hydrogens. This carbon right here, 1, 2 bonds already, so it's going to have 2 hydrogens. And this one over here already has 1 bond, so it's going to have 3 hydrogens. So here we have the complete structure, the condensed structure, and the line-angle structure. And that's really what we're going to be dealing with in this lab. Now, just to kind of indicate what it would look like, I'm going to make this, there we go. We could have a structure like this. And that maybe looks short or kind of confusing, but we can go through and actually look at what is here. So right here, we have C, there's only 1 bond here, so it's got to have 3 hydrogens attached. Then, if we look at this guy, this carbon has got 1, 2 bonds to other carbons, and it's got a Cl, so we're going to write a Cl. And it's got an H down here because 1, 2, 3, 4. Actually, I'm going to put the H first. I think that's the best way and make it a little easier. So it's HCl. Now, that guy is then connected to this one. So that carbon is connected to this carbon. 1, 2 bonds here, so it's got 2 more that are hydrogens because it has to have 4 bonds. Then we're attached to this one, which has got 2 bonds, so it's going to be CH2. I'm probably drawing too large, but that's okay. We'll make it work. Then we're bonded here, where we've got a C, 1, 2, 3 bonds, so it's got an H and an OH bonded to it. And then finally we have this carbon over here, and I'm going to, yeah, I think I can fit. It's got a carbon, it's only got one bond, so there's 3 hydrogens attached. And so you really do get a lot of information here from the line angle. And in fact, you even get some bond information as well because of the way that we draw these. But I'll let you guys cover that in lecture. Oops. Now, it's really not enough to talk about the complete condensed and line angle structures. We also need to be able to name these compounds. So when we name these compounds, there's technically this table in your lab that really gives you the type of functional group, what class of compound it is, and how to name it. And so with that in mind, I'm going to go through these, but I'm going to go through them very quickly. Now, the simplest kind of organic compound is a hydrocarbon. Let's go with purple. Those could be an alkane, an alkene, or an alkyne. They can also be cyclohydrocarbons. Now, alkanes only have single bonds, and they're going to end in an ane. Alkenes have a double bond somewhere, and they'll end in ene. Alkyne is going to have a triple bond. It ends in yne, ine. Cyclohydrocarbons are going to be a closed ring-like structure. Generally, you're going to see 5 and 6 membered rings, but you start with the prefix cyclo. So this has got all single bonds, so it's still going to end in ane, but it's going to start with cyclo. Haloalkanes contain a halogen, so you're going to start with that as a prefix. So if you have a chlorine, it's going to be a chloro. If you have a bromine, it's going to start with bromo. So for example, over here, this is chloroethane. Chloro, and then this is a 2-carbon group attached. Alcohols contain a hydroxyl group, and they're going to have the suffix ol, all. Aldehydes are very similar. They're going to have a carbonyl carbon, which is a double bonded carbon to an oxygen, attached to a hydrogen. And this is very similar in ending. It's al, an ending of al. So while this is methanol, this is ethanal. Same thing here. Ketones end in -one. Carboxylic acids end in oic acid. Esters are probably the one that trips up the most people. Here you're going to name the short suffix, the short side, or the side attached to the oxygen, bridge, and then you're going to name the side after that as well. You're going to name it as an alkyl alkanoate. So this has got an ethyl group, and this has got 4 carbons on the other side of the carbonyl carbon, so it's butanoate. Ethers, there's 2 ways to name ethers. This is probably the one time you don't use the IUPAC name as much. You name one side and then the other, and then you say ether. Or the proper way, which is probably used less often, is to just have, you name one side, and then you name the other is like an alkoxy, and then you name the other side as an alkyl. Now, amines have a nitrogen group attached. They could be primary, secondary, or tertiary. It just depends. But these are going to end in amine, and then amides end in amide. These have the carbonyl carbon and a nitrogen group. So when you're going through the lab, go ahead and write out the structures that are in front of you, and then come back and kind of look through the table and see where you can find where it fits. Now when you're naming, remember that you're going to look for the longest chain of carbon atoms, and it may not be the way that you think. So always go through and make sure you're counting the longest chain. Then you want to use the highest priority to really determine the prefix and suffix of the name. I tried to give those in Table 3 in your pre-lab, so just kind of keep in mind those are a good basis. If more than one of the same substituent is present, you're going to add a prefix to indicate how many of each one is there. Except sometimes you'll exclude mono because it's an understood one. And then you're going to put the number of where the location is for each substituent. Now the idea is you want to get the lowest possible combination. So for example here, this is 1, 2, 3, 4 carbons. If I had a chlorine here, it wouldn't be on the 1, 2, 3 position. Instead it would be 1, 2 because this is the lowest number that we could give it. And then you're going to list all of your substituents alphabetically. So let's do a couple. Let's say we had wrong color. Okay, so let's look at this. Actually, we're going to go like that. No. Sorry. That's not what I meant to do. Yeah, we'll leave it like this for now. So the first thing you want to do is count up the longest chain. So we could say 1, 2, 3, 4, 5, 6. Or 1, 2, 3, 4. No. 1, 2, 3, 4, 5, 6, 7. So technically this is the longest chain. So this has got 7 carbons, so it ends in heptane. 7 carbons means hept, all single bonds means ane. Now we want to look at the substituents. 1, 2, 3, so on the 3 and 4 position we have something, or on the 1, 2, 3, 4, and 5 position. So we don't want to count from this direction, we want to count from here. 1, 2, 3, 4, 5, 6, 7. And so on this third position we have a methyl. And on the fourth position we have a hydroxyl, or an alcohol. So this is a 7-carbon alcohol where we're going to have this substituent at the front. So it's going to be 3-methyl hept, AN for single bonds, and alcohol goes at the back because it's a suffix. So it's 3-methyl heptanol. If, on the other hand, we wanted to do something like this, 1, 2, 3, 4, 5, 6 carbons, that's our longest chain. So that means it's going to have hex in the name. All single bonds, so it ends in ane. And then we have chlorines, 1, 2, 3, 4, and 5 position. Or we could number from this side and have 1, 2, and 3. So we're going to number from the other side and say 2 and 3. Now if we have more than one chlorine, we call it dichloro. Di meaning 2, and then chloro meaning there's both chlorines. So this is 2, 3, dichloro hexane. If you have this is a ketone, so you're going to have the suffix -one. There are 1, 2, 3 carbons here, so it's prop. All single bonds, so it's an, so it's propanone. Technically it's on the second carbon, so you could say 2-propanone, but it's kind of understood. You could also have this. This is a cyclic compound, so it's cyclo. Oops, that should be an L. One, two, three, four, five, six. So it's hex, all single bonds, so it's ane, cyclohexane. If it had a double bond, it would be cyclohexene. Only difference is that one letter. So as you go through the lab, make sure you're paying attention to every little intricate detail about those structures. You want to make sure that you have the structures drawn down completely correct so that you get the right classification. You also need to be careful when you're handling them so that they don't fall apart, because putting them back together may mean that you misplace something and you get the wrong structure back. So just be careful with that.